Yeah, let's continue with the Hurwitz criterion. If the poles of the closed loop transfer function cannot be calculated, or if you want to have very quickly the position of the poles, the stability criterion message, then you should know the Hurwitz criterion. It's one of the very simple criterion you can easily use if the coefficients of the denominator of the transfer function are known. Then you can do this. Mr. Hurwitz is a mathematical scientist. Many years ago, many decades ago, he has worked on this situation and used the following idea. For stability, not the poles are necessary to know, only the sign of the real part of the poles must be known. Then you know something about stability. So it's not necessary to calculate the values of the poles, only the sign of the real part. And for this information, maybe there are other methods, and one method Mr. Hurwitz has found is the following. You look on workbook page 35, there we can see the conditions for the Hurwitz criterion. I think this is the best way to do this presentation. So you see workbook page 35, stability criteria. Here again the pole criterion is called, and here you see the Hurwitz criterion. Just half a page, very simple. Note the denominator is responsible for stability, so the numerator is not necessary to know. Then we in this block get information about the signs of the coefficients. To avoid problems if all signs are negative, note that then you can extract the minus sign of the denominator and put it into the numerator. So if all signs are negative, put the sign in the numerator, then all signs are positive. Now look for this box. The Hurwitz criterion postulates 3 sub-criterion. The first criterion is very simple and very helpful. If you know this, then sometimes you can exactly check stability with one view on the coefficients of the denominator. A system with given closed loop transfer function is stable if and only if the denominator has the following characteristics. 1. All coefficients must be positive and unequal to 0. So the 0 condition is also not allowed for stability. Of course, higher coefficients. Yeah, if the highest coefficient is n, of course n plus 1 is 0. That is of course not meant, but if the coefficient Cn is existing, all other coefficients with lower index numbers must be positive and should not be 0. This can be checked with one view on the coefficients, but that is not sufficient. That is a necessary condition, but not necessary and sufficient. So we can have to go then, if this is true, again, positive means if all negative, extract the minus sign, and then they are all positive. So in other words, they should not have uneven different signs. If there is one minus sign, negative coefficient, and one positive coefficient, this is violated, and condition 1 shows that this system becomes unstable. If this is true, if condition 1 is true, then second condition is also be necessary. The Hurwitz determinant must be positive and unequal to 0, and this is also not sufficient. All northwest or top left subdeterminants must also be positive and unequal to 0. So this deals with the so-called Hurwitz determinant, and this is defined here. So make it a little bit larger. What is the Hurwitz determinant? The Hurwitz determinant has an index n. N is the degree of the highest p in the denominator. N is the degree of the denominator. The Hurwitz determinant has an n times n, so n columns and rows determinant. In a third order system, you get a third order 3 times 3 determinant. The filling law is the following, and this is the invention of Mr. Hurwitz. Filling law is start with the top left cell with Cn minus 1. It is the second coefficient, here in this order. Then the next cell with n minus 3, next cell n minus 5, next cell n minus 7, and so on. So you see only half of the coefficients are listed here. The other cells, which leave 3, are set to 0. The second row exactly gets the other coefficients, starting with Cn, Cn minus 2, Cn minus 4, Cn minus 6, and so on. Again, half of the coefficients are listed here. You have n cells, so the rest of the cells which are not covered with these elements are set to 0. Third row is starting with a 0, and then this is a copy of the first row. Fourth row is a copy of the second row shifted 1 cell to the right. Fifth row is the third row shifted 1 cell to the right. Sixth row is the fourth row shifted 1 cell to the right, and so on. So this is a simple order. If you have one time done this, I think you can understand the filling rule. It's rather very simple. This calculation of the determinant can be done for any order. So 1000 times 1000 determinant can be calculated, and it must be checked if this is positive and not 0. And furthermore, the subdeterminant, so I say the top left. I should copy this determinant into my notepad. Sorry, wait for this. So this is the copy of the determinant. The top left Hurwitz determinant, then this 2 times 2 top left, 3 times 3 top left, and so on. Any of these top left subdeterminants also must be positive and should not be 0 for all determinants. So if then this is true, then you can be sure that if 1, 2, and 3 are true, then the system is stable. If one of these conditions is violated, system is unstable. So I think this is a very quick check we can now execute in many examples. For this, of course, you have to know something about how to calculate a determinant. With a handheld calculator, of course, you can do this, but note the problem appears if the Cn's like T1, T2, T3 are not known as numbers, but are unknowns like time constants. Then, of course, you need a method to calculate determinant values with a general method. And I think if we go to orders up to 4 and 5, then of course you can see what I mean. Okay, let's do some examples. Yeah, the first example for 4, yeah, example chapter 4, number 4, is my rocket example. The position control of a rocket or satellite can easily be checked. The question I want to answer is, can the position of a satellite be controlled with a P controller? Okay, very quickly. A rocket with a mass m or satellite has a position x, and there is a very simple law for this relation between position and mass, caused by the Newton's law, is F is mass times acceleration, and acceleration is the second derivative to the position. And if I want to have the process signal block diagram, you will see very quickly what I mean. The position depends on the driving force. Yeah, if you have here a rocket, know that this caused a force to my rocket. If the driving force appears to my mass, then the position is calculatable with, very simple, the following method. So make 2 times integration of this equation gives x is f divided by m, double integral, sorry, f is a dynamic value, dynamic variable, f d t dt. So this is a double integrating process. So if you apply a force to a flying mass, then the position changed with double integration. This is also true if you control the direction of a boat, or if you just move any, if you fly in a quadrocopter. These are the laws of flying objects or swimming objects. Now the question is, can I now control this process with a simple P controller? The question can easily be developed, and you will see very quickly decided if this is possible or not. We make a negative feedback with a closed loop system with this process 1 over m and 1, 1 over m and 1. You can say the open loop is nothing else than k divided by m divided by p squared. Note that an integrator is 1 over p, 2 integrators 1 over p squared. The closed loop transfer function then is open loop k divided by mp squared 1 plus k divided by mass p squared. And you'll see that if I simplify this expression, then I get k divided by m p squared plus k divided by m. This is a closed loop transfer function. And note stability with the rules of Hurwitz needs, this is n2. So C2 is 1, C1 is 0, and C0 is k over m. So we can say, okay, in red, this is a violation. So we know this is unstable because the coefficient C index 1 is missing. So without any calculation of poles and any other things and determinants and what else, you see the transfer function here has no C1, and then at once you can say, okay, with a P controller, a flying object cannot be controlled. In other words, you need better dynamical controllers like a PD or a PID, then this can be done, of course. But a simple P is not possible. Okay, more examples. Yeah, in a paper called Exercises or Exercise 2006 PDF, you can find in your Moodle course on page 8, you can find a list of polynomial functions. These polynomial functions should be the denominator of a system. So we have to investigate these polynomial functions with the Hurwitz criterion, and if then all three conditions of Hurwitz are true, the system with this denominator is stable or not. So let's start with the first one. Paper Exercises, page 8. This is, you can see n is 3, C3 is 1, C2 is 6, C1 is 12, and C0 is 8. Of course, I can tell you, of course it is possible to calculate the values of the poles, because the C's are given as numbers. But of course we want to first check this with the Hurwitz criterion. First condition of Hurwitz is check if n is 3, but if with C2, C1, C0, you see all coefficients are positive, all Ci positive, and all Ci not 0, for starting with C3. So the first condition is true, so I have now to calculate the Hn, the H3 determinant, which has 3 rows and 3 columns, indicating with dotted lines. I think then you can follow my my discussions. Start with Cn minus 1. If n is 3, this is C2, C0, this is C3, and C1. So I write down, starting with a second coefficient here with 6, followed by 8. Then there are no other coefficients, so this next is a 0. Then starting with the highest coefficient, which is 1, and then the over next is 12, followed by no other coefficient available is 0. Then the third line is the first line shifted one cell right, is 6, 8, and now we are ready. So we can calculate now the determinant, and now note we have a development rule. A development rule of determinants can be used to reduce a 3 times 3 determinant into 2 times 2 determinants, using the development to one row or one column. I will do this now in more detail. I develop the determinant relating to this column, so the third column. This cost gives the following result. This coefficient is 0 multiplied with a determinant which comes out of the 3 times 3 determinant by cancelling this row and this column. So this is the final 11206. I think you have learned this in mathematical basic lessons. Followed by a negative second coefficient. The signs of this addition, the signs comes from the chessboard, plus, minus, yeah, in changing order. So this is plus, minus, negative sign, this coefficient multiplied with the determinant which is the rest if you cancel this row and this column. So this is 6806, 6806, followed by plus this coefficient 8 times the determinant, which comes out if you cancel this row and this column, is 68112. 68112. Of course, yeah, these both parts are 0 because the coefficients are 0, so the development should be done to that row or column which carries the most of zeros. And we have now the last calculation. This is 8 times, and 2 times 2 determinant is 6 times 12 minus 8 times 1. 6 times 12 minus 8 times 1. You can see we don't need the value. We can see 6 times 12 is larger than 8 times 1, so we can at once say, okay, this is positive 0, this is okay. So the third condition is valid. So I first show you very detailed the third condition. Third condition. Go back to the page 35 of my paper. Wrong page. Workbook. All CI must be positive. That's okay. Hurwitz determinant positive and unequal to 0 is checked, is okay. Now the third condition, all northwest subdeterminants. What are these subdeterminants? First we have H1 is the subdeterminant 1 times 1, so that is just the top left cell. This is always Cn minus 1. This must be positive and unequal to 0, otherwise the first condition is violated, so no new information. If this would be negative and this condition is heard, then condition 1 was heard, and so we can stop earlier, so no new information. H2 is now the subdeterminant top left, northwest, we can say, is 6, 8 times 112, and this you see we have already checked. This is larger than 0, so all conditions are true. So system with this denominator is stable. Check. We now compare the result of Hurwitz with the pole criterion. So we can, of course, the coefficients are given as numbers. We can just type this into a pole 0 finder, and then we can check that all poles are equal or minus 2. Or in other words, if you check this, this is stable. Or if you calculate p plus 2 3 times, then you get p to the power of 3 plus 6p to the power of 2 plus 12p plus 8, our starting condition. So of course the pole criterion and the Hurwitz of course must deliver the exact same statement. Okay, next examples in next video.